In this video, I'm going to solve 3 or 4 kinematic problems in 2D, so mostly projectile motion problems. And then I'll have another video where I do some uniform circular motion problems for the chapter on 2D kinematics. So we're going to start with this problem. A projectile is launched at ground level with an initial speed of 50 meters per second at an angle of 30 degrees above the horizontal. It strikes a target above the ground 3 seconds later. What are the x and y distances from where the projectile was launched to where it lands? So the first thing I always do is I take what I'm given, my magnitude and my direction, and I find my components. So it gave me an initial speed, so initial magnitude of velocity is 50 meters per second. And it gave me an angle of 30 degrees above horizontal. So I always like to draw a separate triangle for my components. So that's this angle. This is V0, my magnitude. The vertical leg will be my y component of initial velocity, and the horizontal leg will be my x component of initial velocity. Okay, it's really important not to write x and y as your legs, because this is a velocity and these must also be velocities, so these are distances. So don't just write x and y. This is bad. Okay, your vector, if it is a velocity, it will have velocity components, so your legs need to match the actual vector that you have. Okay, so that's a mistake that we often see. And so now that I have this written this way, I can write this as my opposite side. This is my adjacent side. The magnitude is always my hypotenuse. And so the first thing I'm going to do is get my components. So sine is opposite over hypotenuse. So for us that is V0 y over v. So this gives me V0 y is v, should be not, V0 sine theta. And if I do the same for cosine, so maybe I move this down a bit, save some room. Cosine will be adjacent over hypotenuse, or V0 x. Typically, once you know one, you immediately know the other. V0 cosine theta. Okay. Now you could, at this point, solve for V0 y and V0 x. Some people like to do that. I'm not going to do it just yet, but you could absolutely plug that into your calculator at this point. I'm going to leave it be for now. So now I'm going to write down the rest of what I'm given, or what I know about the problem. So it gives me a time of 3 seconds, so time equals 3.00 seconds. And since this is an object that's in projectile motion, okay, it even tells me it is a projectile, I'm going to write down my accelerations because I always know that these are true. So I always want to write these down. Okay? And it's asking me for my x and y distances, so it wants me to find delta x and delta y. Okay, so this is what we want. Okay? Well, if you remember my video on 2D kinematics where we talk about projectile motion, there is only one equation that gives you any new information in the x direction, and that is delta x equals V0 x times time. Okay, and we get this equation because our acceleration in the x direction is 0. So I know V0 x is just V0 cosine theta. So instead of writing V0 x, I'm going to write V0 cosine of theta and multiply that by time. Okay, so you could go ahead and find your value and plug it in in multiple steps. I like to do things all at once. So 50 meters per second times cosine of 30 degrees. This will give me my v naught x, and then I multiply by 3 seconds, and I get delta x equals 130 meters. Okay. And then if I'm given time, and I know the initial y component of velocity, then that means I should use this kinematic equation for y, so the exact same one that we used for x. So we get minus 1/2 gt squared. Okay, so this, again for v naught y, I'm going to plug in v naught sine theta. So I'm just going to punch in the numbers, 50 meters per second times sine theta, or sine of 30 degrees, times my 3 seconds. And I'm going to run out of room, but I'll write this down here, minus 1/2 g, which is 9.8 meters per second squared, times my 3 seconds all squared. And if you punch that in, you should get 31 meters for your delta y. Okay, next problem, a kickball, or next problem, a ball kicked with an initial velocity of 16 meters per second in the horizontal direction and 12 meters per second in the vertical direction. At what speed does the ball hit the ground? For how long does the ball remain in the air? And what is the maximum height that is attained by the ball? Okay, so first off, I want to write what I'm given. It gave me an initial velocity, so I know that's a v naught, and it's in the horizontal direction, so I know that's the x component of initial velocity, 16 meters per second, and then 12 meters per second in the vertical direction, so v naught y is 12 meters per second. And I'm going to draw a picture, maybe just a small one. I find it useful. Okay, so it's going to hit the ground some distance away. This is my angle it's launched at. And for the first part, it asks, at what speed does the ball hit the ground? So I'm going to use what I know about projectile motion. In the x direction, there is no acceleration. So the x component of velocity, when it hits the ground, is going to be the same as it was when it left. So the x component won't change. Now, when it gets to its maximum height, all of the velocity is in the x direction, and the y component of velocity is 0. If it hits the ground at the same height as it was launched, then it will accelerate for the same amount on the way up as it does on the way down. So my y component of velocity is just going to be minus the initial y component of velocity. Okay? So this is always true. So always true in projectile motion. And this is true when your object lands at the same height at which it was launched. Okay? So if I want to find the speed is code for magnitude, and magnitude means use Pythagorean theorem. Okay, so the magnitude of my velocity is my speed, and that's vx squared plus vy squared. Okay. Well, I said my vx is the same as v naught x, and my vy is just minus v naught y. So I can plug in 16 meters per second for x and minus 12 meters per second for y. And I find my magnitude is 20 meters per second when it hits the ground. Okay, so that's part A. For part B, it asks for how long does the ball remain in the air. Okay. Well, I know Vy when it hits the ground. I know V naught y that it started at. So if I look at my first kinematic equation, or my easy one, what I call the easy kinematic equation because it's the shortest, I know Vy, I know V naught y, right? That was this argument. And then I know the value of g, and I'm looking for time. So I can just rearrange this for time. I'm going to move my V naught y over by subtracting. So Vy minus V naught y. And then I'm going to be left with a minus gt, so I'm going to divide by minus g to get t by itself. And if I plug this in, I said Vy is minus 12 meters per second at the end. And I started at a positive 12 meters per second, so minus positive 12, divided by minus 9.8 meters per second squared. If I plug this in carefully, I should get 2.45 seconds. Okay? So in all of your equations where you have time, you have to be careful. This time, because I put the velocity at the beginning and the velocity at the very end, that means this time corresponds to my total time in the air. Had I put the velocity initially and the velocity at the top of my trajectory, then this time would correspond to the time it takes to get to the maximum height. So the time in this equation will always correspond to which 2 points you put in for the velocity. So that's something you want to keep in mind. So for part C, we're going to be finding the maximum height attained by the ball. Okay, so we need one of our equations that has delta y in it. Okay. And I don't know the time it takes to get to the max height. I could find it very easily. So I don't want to use the one with time. I'm going to use the other kinematic equation that has delta y in it. And that is this one, Vy squared equals V naught y squared minus 2g delta y. And if I solve, first of all, I have Vy equals 0 at the top because I'm asked for the maximum height. So I can get rid of that. Then I want to solve for delta y. So I'm going to move this whole thing to the other side since it's negative and make it 2g delta y equals V naught y squared. And then to get delta y by itself, I just need to divide by 2g on both sides. So this is going to be 12 meters per second, all squared over 2 times 9.8 meters per second squared. Punch that in carefully, and you should get 7.35 meters. Okay? So the next problem, a basketball player is running at 5 meters per second directly toward the basket. When he jumps into the air to dunk the ball, he maintains his horizontal velocity. What vertical velocity does he need to rise 0.75 meters above the floor? Okay, and then we want to find how far does from the basket, or the horizontal distance, must he start his jump to reach his maximum height at the same time that he reaches the basket. Okay, so first off, let's write what we know. He's running 5 meters per second toward the basket, so horizontally. He's running across the court. So this is his horizontal velocity. Okay. And then we know he's going to jump a distance of 0.75 meters, and since he's jumping up, this is a delta y. Okay. Now, first we're asked for his vertical velocity. What vertical velocity does he need to get this high? Okay. So, when he's at the top of his jump, we know something to be true. We know that the velocity in the y direction must be 0 because that's when he's going to stop going up. So we know Vy equals 0, and we know delta y. Okay, so if we look at our equations, when we get to this one, first of all, we have no time. We don't know anything about the time, and 2 of our kinematic equations have time in them. Okay, so we should start by looking at the one that doesn't have time. And when we do that, we can plug in Vy is equal to 0. We're looking for V naught y, and we know delta y. And we know the value of g, so this is the kinematic equation we want to use. So I'm going to move this to the other side and make it positive. So that's going to give me V naught y squared equals 2g delta y. And then I need to take the square root of both sides to solve for V naught y. And then I can plug in my values, 2 times 9.8 meters per second squared times my delta y value. And that gives me 3.83 meters per second. Okay. Okay, so now I can move on to part B. How far from the basket? So how far horizontally? So at this point, it says how far, and it kind of gives me a hint. So I know I'm looking for delta x. So how far horizontally must he jump to reach his maximum height at the same time? Okay. So we need to know the time because it says the same time, but we don't know what that is. So the first thing I'm going to do is solve for time. Okay, and so I want to see if I can use my easy equation, V naught y Vy equals V naught y minus gt. I know at the top of his jump, Vy equals 0. And I just found V naught y, so I can find t, in this case t to max height, just by rearranging. So if I move minus gt to the other side and divide by g, I get my expression for time. And so I'll plug in my 3.83 meters per second that I just found, divide by 9.8 meters per second squared, and I find he's in the air for 0.39 seconds. Now that I know time, there is only one kinematic equation that gives me anything in the x direction. Delta x equals V naught x times time. It gave me V naught x in the very beginning, and now that I have time, I have everything I need to solve for delta x. So plug in 5 meters per second times 0.39 seconds. And I find that he needs to jump when he is 1.95 meters back. Okay, this is the last problem for projectile motion. A ball rolls off a table that is 0.9 meters tall and it lands 1.1 meters horizontally from the edge of the table. Find the total time the ball is in the air and find the magnitude of the initial velocity, and then find the magnitude of velocity just before the ball strikes. Okay, so I want to write down everything I know. First, it falls off a table that is 0.9 meters tall. So delta y is 0.900 meters. And it lands 1.1 meters horizontally. So horizontally tells us delta x. Okay. And this is really important. It's falling, if I draw a picture, it's going to start up high and it's going to fall down. So my delta y value, since the position is changing downward, it needs to be negative. Okay? So this is my delta x in my picture, and this is my delta y. Okay? So for part A, I'm looking for the total time the ball is in the air, so t total. And I know, just from drawing my picture, the ball is initially rolling horizontally. So that means all the velocity is initially in the x direction, so the initial velocity in the y direction must be 0. Okay? And a lot of times your time is associated with the y direction. The time you're in the air depends on your y component. Okay? So if I look at my equations, I want to find how fast I'm going at the bottom. So right now I don't have enough information to solve for time just yet. But if I look at my equations, if I only had the final y velocity when the ball lands, then I can solve for the time. So I want to go to the one equation that doesn't have time and get my y component of final velocity. So I'm going to plug in v naught y equals 0. And then I need to take the square root of both sides. So Vy is square root of minus 2g delta y. And this is why it's really important for your displacement to be negative, because I have a negative sign under my square root. But because it's falling and delta y is negative, that's okay. Plug this in. And if I do all that, I should get a value of 4.2 meters per second. And then when I took the square root, I really have two values. And so since I know physically it has to be going down, okay, when something falls, it's never going to start going more up. It's always going to be going down. So my velocity is going to be negative. Okay? And I just know that conceptually and contextually from the problem and from what objects do when they fall. Okay? So now I can go to my next kinematic equation. So this is part 1 for second step, or second part. I can go to my easy kinematic equation, or my short one. I just found Vy, and I know V naught y is 0. So I can solve for time pretty easily just by dividing by minus g. So Vy divided by minus g. We said this is negative, so negative 4.2 meters per second over minus 9.8 meters per second squared. And this is 0.43 seconds. So you can see it was a good thing that we had these two minus signs, because our time should be a positive number. Okay, so for part B, find the magnitude of initial velocity. So first off, our initial velocity, we said, is all in the x direction. Okay, we only have one equation that gets us anything in the x direction, and that's delta x equals v naught x times time. We know delta x, it was given to us from the start, and we just found the time that it was in the air. So we have everything that we need to solve for v naught x. So I'm going to divide by time on both sides. And this is 1.1 meters over 0.43 seconds. And so its initial speed was 2.56 meters per second. Okay, so for part C, we're asked to find the magnitude of velocity just before the ball strikes. So again, using what we know Vx is always going to stay the same, and we just found it in part B. So we already know that. And then we found Vy in part A on our way to get the time. So we know Vy is just minus 4.2 meters per second. So when it asks for magnitude, that means we should always think Pythagorean theorem. So square root of Vx squared plus Vy squared, or square root of 2.56 meters per second from part B, and minus 4.2 meters per second from part A. Plug all this in and you should get a magnitude of 4.9 meters per second. So hopefully these projectile motion problems helped you a little bit in figuring out what you're given, what you're looking for, how to decide which equations to go through. If not, go back, slow them down, and rewind and see if you can look through your equations and make those decisions. And I'll be posting another video that has some uniform circular motion problems.